Hello people, welcome to Gurukula. I'm Jai. So today in this video we are going to see about the topic variable length subnetting. So without any further delay, let's get into the topic. So when you want to understand the variable length subnetting, so here it is very much important to understand about something called as subnet mask. So we will see what exactly mask is, and from the word mask we very well know that this is what a mask is meant to be. So we will try to understand what is subnet mask with the same approach what we know. So when you look at this particular mask, you can see that this is a face mask which is going to cover the actual face, and then there is going to be a small opening like this, so that the entire face is going to be covered by some part of the mask like this, and then some part of the face will be left open like this. The same thing we are going to use it for our IP addresses as well. So we are going to use the same mask like this, whereas one part of the subnet mask will tell us what is the network ID, and then some part of the mask like this is going to tell me what is the host ID. So in order to identify what is the net ID and host ID and all other similar purposes can be identified by using the subnet mask. So with this approach we will try to understand what subnet mask is. So subnet mask is also a 32-bit number which is actually we are going to mask it on an IP address, and this particular mask will divide the IP address into network address and then the host address. So subnet mask is made by setting all the network bits will has to be represented with 1 and all the host bits has to be represented with 0. So your subnet mask, all the bits that is used to represent the network should be given as 1, and all the bits which is used to represent the host should be taken as 0. So with this you can see an example of a subnet mask. So here you can see a class A, class B, class C kind of IP addresses. So here as far as class A is concerned, we very well know that the first 8 bits is representing the network ID, and then the last 24 bits is representing the host ID. So when I try to write the subnet mask for class A address, as you can see, the first byte represents the net ID. As we very well know, the network part has to be represented with 1, and then the host part has to be represented with 0. So as far as class A is concerned, the first 8-bit represents network part, so it is represented as all ones over here, and then the remaining 24 bits represents the host part as shown like this. So host has to be represented with 0, so there is all zeros over here. So this is a binary representation, and when you convert this to decimal, dotted decimal representation, we will be getting that 255.0.0.0. So now this will be the default subnet mask. This will be the default subnet mask as far as class A is concerned. So similarly for class B, you can see that as far as class B is concerned, 16 bits is meant for net ID and 16 bits is meant for host ID. So 16 bits I will have to mark as 1, and then 16 bits I will have to mark as 0. So we will be getting 255.255.0.0. So this is the default subnet mask for class B is concerned. And similarly for class C, the default mask would be 255.255.255.0. So this subnet mask will help the system to identify that how many number of bits is allocated to represent the network and how many number of bits is allocated to represent the host. And also if a system sees that the subnet mask is 255.0.0.0, then it understands that this is by default belonging to class A address and there is no subnetting performed because we are allocating only 8 bits to represent the network. In case if we are subnetting, then definitely we might have borrowed certain amount of bits from the host ID. So obviously these bits will be represented as 1. So there will be a difference in the number of ones in the default subnet. So by using this subnet mask, we can identify, or the system will get to know that the subnetting has been performed over here. And then there are multiple ways of representing the subnet mask. So how do we represent the subnet mask? There are three types of representation. The first type is binary representation, what we have seen in the previous slide, and then the next one is dotted decimal representation, which is also seen in the previous slide. Another representation is /n representation, whereas n represents number of bits allocated for a network. Let's take for an example, if it is class A, 8 bits will be allocated for network bits. So what we can do is, I can write any class A address like this, 10.10.1.5/8. So this /8 represents that 8 number of bits out of this 32-bit is allocated to represent a network. So we very well know that since it is starting with 10, this belongs to class A address, and in this class A, this out of 32-bit, 8 bits which is present over here is meant for representing the network. So a default subnet mask for all the class A, class B, class C is represented over here. So this table will give you a clear understanding of what is the default subnet mask for each and every classes that you see. And then this is the dotted decimal representation and /n representation for the same class A, class B and class C. So if there is no subnetting performed, then the default /n representation for class A is /8, and for class B is /16, and for class C is /24. So what happens when we perform a subnetting? So let's try to understand the need for subnet mask first. So given any IP address, a subnet mask can be used to identify the network ID. So we can easily find out the network ID. So if subnetting is not performed, then identifying the network ID is very much easier. Let's take for an example, I have an IP address like this, 10.10.2.1. So we very well know that this is class A. So this is going to be kept constant, and the remaining things I will have to put it 0. So this represents the net ID of the given IP address. So this explanation is valid only if there is no subnetting is performed. In case if I am using a class full address, say for an example, let us assume that this IP address is from the subnetted address space. So in that case, we cannot identify the network ID of that particular address. So there we will be using the subnet mask. So as you can see, this is the given IP address. This is what the given IP address is. Here the IP address that we have taken is 192.168.1.5. So when I put an binary representation of this IP addresses, I will get this particular table. And then we very well know that this belongs to class C IP address, and for class C IP address we can have the first 3 bytes of information that represents the net ID, and then the last byte of information represents the host ID. So in the subnet mask, we will have to put all ones that representing the network, and we will have to put all zeros that represents the host. So my subnet mask will be 255.255.255.0. Now you will have to perform a bitwise AND operation between the subnet mask and then the IP address, which will give you the network ID of the given address space. So that is how you can easily calculate the network address of any given IP address. And remember, there must be an information given along with this IP address that if there is any subnetting performed, then the number of bits allocated for subnetting should also be given. Only then the network ID can be calculated. So let's go back to the previous problem. Here I am not going to get back to the previous problem. You can refer to my previous slides on variable fixed length subnetting, where you can see the example approach. So in order to perform the routing, that is subnetting is performed. So what we will have to do is we will have to perform, or I will have to borrow 1 bit. So this is what the IP address which we have discussed in the previous videos, and then we have subnetted the entire address space. So the given address space is 200.1.2.0. This is what the given address space is, and we further classified or subdivided this particular address space into two address space. So this is what the first address space that belongs to net 1, and we subdivided this into net 2 as well. So this is what net 1 is. So your net 1 will runs from dot 0 to dot 127, and then you can see that since we are dividing it into 2 net, then definitely we need 1 bit from the host side in order to group it into two different network. So where you can very well see that there is 1 bit occupied from the next side. So what will happen, the subnet mask, all the bits that we were using to represent the network should be kept as 1. So even though this particular bit belongs to the host part, we are taking this 1 bit to represent the network. So subnet mask will have to be written as including this particular one. So now by converting this binary representation to dotted decimal representation, you will get 255 for all ones here, 255 for all ones, and 255 for all ones, and this 1 followed by 7 zeros will give you 128. So this will be the subnet mask for the subnetted ID. And you can very well see that there is an /n representation. Generally for class C, the /n representation will be 24, which means that 24 bits will be allocated for representing the network. But here we are subnetting the given address space. Correct. So this 24 bits we are not altering. The bits which is left side to this particular line we are not altering, but we are taking one more additional bit here for subnetting purposes. Somehow or the other way we are using this bit also to represent the network. So totally we are using 24 bits plus 1 bit, which is 25 bits we are using it to represent the network part. So /25 is being represented over here. So this is what we call it as subnet mask, which has to be represented everywhere where subnetting is performed. So this is an subnetting master table which will be helpful for you to solve problems on the subnetting. So you can take a screenshot and you can make use of it whenever we solve problems on the subnetting. So now we go for variable length subnetting. The actual topic of today's video is what variable length subnetting. So in variable length subnetting, there are certain drawbacks with the fixed method. So what are all the drawbacks that is existing in the fixed length subnetting? So all the subnets will have equal number of IP addresses, correct? So what we have seen in the previous case, you might have seen that when the address space is divided like this, all the subnets that we divided will have equal number of IP addresses. But what if I need to divide the network like this, which has variable number of IP addresses? Whereas for one department I should use 64 IP addresses, another department I should use 64, and whereas one department I should use 128 IP addresses. So here in this cases we cannot use fixed length subnetting. So this is where actually variable length subnetting is coming into the picture. So your variable length subnetting may sometimes be also referred to as variable length subnet masking, which is VLSM. And also it will be referred to as classless interdomain routing, which will be also called as CIDR. So classless interdomain routing can also be the term which is used to represent the variable length subnetting. So let us take an example and then we will try to understand how exactly the variable length subnetting will be working on. So the given question is, you are expected to divide the given address space, that is 172.16.0.0/16. So /16 represents that it is an class B address. Right. So class B address, and we very well know that there is no subnetting performed in this particular class of IP addresses. And then we are expected to divide this as 7 networks. And also in each and every network, for network 1, you will have to have 500 hosts. For network 2, you will have to connect 200 hosts. So this is the requirement given by the system administrator also. So we will have to perform a subnet, or we will have to divide this one entire address space into 7 networks, and each and every network must have this particular requirements connected in it. So let us see how to perform this particular task step by step. So please pay kind attention from this particular slide. So each and every step involved here in variable length framing is very much important. So the first and foremost step that we wanted to perform is arrange the required number of hosts in ascending order. Actually, that should be arranged in the descending order. I'm sorry for the typo. That has to be arranged in descending order, which means the largest number first, starting from the smaller and keeps on smaller. So this is what the maximum number of hosts that I required. So maximum number of hosts I require is 500, so I place it in the first part, and then the second lowest requirement is 200, next lowest requirement is 100, and next lowest requirement is 60, 20, 2 and 2. So this is how I will have to arrange the host requirement first, and then what I will have to do is allocate the number of bits required for host in powers of 2. Whereas in fixed length framing, you might have remembered that we might have divided the network from the network part. But here we are fixing the number of bits that is required from the host part. So in order to connect 500 PCs, how many number of bits I require? So 2 to the power of 9 will give us 512. And in IP address there must be a logic. Everything that you can divide can be divided only in the powers of 2. Correct. So the closest value for 500 what we get in 2 power something is 512. So 2 to the power of 9 will give us 512. Similarly, you will have to do it for the other requirements as well. So we cannot go for exactly 200 systems or 200 IP addresses. We will have to go for 256 block. And for 100 it is 2 power 7, which gives us 128, and for 60 it should have 2 power 6, which is 64, and for 20 you cannot divide 20 exactly, but you can divide it as 2 power 5, which is 32, and 2 power 1 gives you 2, but still there is an limitation in the IP addresses that when you divide a block, then in that particular block 2 IP addresses becomes unusable. Correct. Let's take for an example, if this is the IP address block that we have, then obviously the first IP address is meant for network ID, which is not usable, and then the last IP address will be used for broadcast. So this is also not usable for assigning to the host. But whereas in the question it is given like there must be 2 hosts to be connected in that particular network. So if you exactly divide with 2, obviously I will end up with 2 IP addresses, and those 2 IP addresses will be left unusable. So that what I will have to do is, there is a little bit of common sense, we'll have to work it out here. So we will have to use 4 IP addresses over here. Even though 2 IP address can be possible to create, but we should not create that, because those 2 IP addresses will be assigned for net ID and broadcast ID for default, which may end up, or it may result in no host can be connected to that particular subnet. So we will have to take 4 IP addresses. I think this makes sense. Fine. So once step 2 is done, then we can move for the next step. So what we'll have to do is write the given address space with required number of host bits. So what I can do is I can count for the required number of bits from the right side and find the first and last addresses. So as you can very well see, I will have, this is what the address space given in our question. So for the sake of simplicity, I am taking first 2 as decimal representation. We are going to work with the last 2 parts so that I am representing this in the binary form. This is purely for the sake of understanding and for the sake of reducing the writing work. So what I will have to do is, now I very well know in order to connect 500 hosts, I need 9 bits in total. So 9 bits I will have to allocate for the host part. So as you can see, the first 8 is allocated, and then one more bit from the network, one more bit is taken for Totally 9 bits is taken for representing the host. So this 9 bits will give us the possibility to connect 512 bits. Even though the 2 IP addresses goes in unusable, remaining I will be left with 510 IP addresses. However, I am going to use only 500 hosts. So this is sufficient. So then what I will have to do is I will have to find the last address. So if all zeros, the 9 bits of zeros is the first address, then 9 bits of 1 will be the last address, keeping the black part unaltered. Right. So what we can do is I can now convert this into decimal form. So this is what the decimal form is. So what is happening? So as you can see, 172.16. This represents 0, and then so /23 represents the number of bits that we have used for representing the network. So if we reduce 9 number of bits, we have left 9 number of bits here in the red color part for representing the host. So how many bits is left for us here in the network part? Here already I have 8, here I already have 8, and here I have 1, 2, 3, 4, 5, 6 and 7. So I have 7 bits here. So 8 plus 8 is 16. So 16 plus 7 is 23. So 23 number of bits is there to allocate the network, or 23 number of bits is allocated to represent the network part. So /23 will be represented over here, and you very well know that this is /n representation of the subnet mask. And similarly for the last address, 172.16.1.255. So that is what the decimal representation of the address what we have in the left hand side. And then the next step is what you will have to do is write the immediate IP address, immediate next IP address of the previous IP address. Now you have this, correct? Now we have 172.16, all zeros 1 and all ones. So this IP address is what allocated, this address space is allocated for net 1. So what we will have to do? We will have to write the next IP address of this. What is the next IP address? You just add a binary 1 here and then you perform the addition operation. So obviously what you will get after 255? It will be 172.16. If I add 1 here, this becomes 0. Correct? And this becomes 2. So 2.0. This is what will be my next IP address. So that is what written over here. Correct? Fine. So now what you can do is, now you will have to repeat the same procedure again. Now the number of bits that is required for the host part is varying. Earlier we required 9 number of bits for representing the host, but now only 8 bits is enough to represent the host. So what I will have to do is I will highlight only the 8 number of bits. This time only 8 number of bits is enough for me to represent the host, because I am going to connect only 200 hosts. So what I will have to do is I will have to keep the network part constant, which means the black color part has to be kept constant, and then the red color part has to be varied up to the last number, which means all ones has to be replaced. So my IP address block will vary from all zeros to all 1. You can observe that the red color is varying from all zeros to all 1. So this time if you convert this into decimal part, what you will get? You will get 172.16.2.0, and then /24. You can observe that it has changed to /24. How is it 24? This 24 represents number of bits allocated to represent network part. So here it is 8 bits, here it is 8 bit, and here it is again 8 bit. So 3 times 8 gives us 24, which represents that 24 bits is being used to represent the network part. And similarly for the last IP address, you will get 172.16.2.255/24. Correct. So what is the next step? We will have to write the immediate next IP addresses. You will have to repeat the same procedure until the last subnet. So what is the next IP address of this? You will have to add 1 here. So if I add 1, what will I get? I will get 172.16.3.0. This will be my next IP address. So I will write that in binary representation here. And then how many number of bits I require now for this? I need only 7 number of bits to represent the host. So 7 bits is highlighted in the red. So red color represents the host part and black color represents the network part. So what I will have to do, I will have to find out the last address, and this is what my last address is. And obviously what will be the /n representation, you can pause the video here and then you can take a guess. So I have 8 bits over here, I have 8 bits over here, and I have 8 bits over here, and I have one more bit over here which is allocated to represent the network. So 3 cross 8 is 24, so 24 plus 1 is 25. So /n representation should be 25. So yes, it is 25. So 25 number of bits is allocated for representing the network part, and similarly last address has to be written. Though the same procedure should be followed for all the remaining subnets. So I will reveal the answers now. You can freeze the video over here and then you can just try to understand how the process is getting over here. At this point in time, if you have any doubts, you can please do mention your doubts in the comment section. I will be answering it. So with this, we have finally divided the subnet mask over here. So the given address space is divided into 7 subnets, and you can clearly notice that the number of bits used for representing the network is keep on varying over here. Earlier for the first subnet it is 23, for the second subnet it is 24, for the third subnet it is 25, and next it is 26, 27, 30 and then 30, where you can clearly see that the number of bits required for representing the network is keep on varying. So this is where you can clearly say that it is what variable length subnet masking or variable length subnetting. And also you can notice that the wastage of IP addresses is also greatly reduced in this variable length subnetting. So where you can see over here, I am going to connect 60 number of hosts in this particular subnet. Even though this particular subnet has 64 IP addresses, out of 64, 2 IP address will be left for network ID and then the broadcast ID. So remaining I will be left with 62 IP addresses. And out of 62 IP addresses, I am going to connect 60 hosts in that particular network as given in the requirement. So the wastage over here is only 2 IP addresses. Only 2 IP addresses will be wasted as far as variable length subnetting is concerned. So when you take the previous video and then if you do the same check there, you can clearly see that there are a hell lot of IP addresses getting wasted in fixed length subnetting. And also we do not have the freedom of connecting different number of hosts in that fixed length subnetting. So that is why we go for variable length subnetting. And of course this may not be understood at one example. We will take it an another example and then we will try to solve over here. So this is another example where we are expected to divide the given address space into 3 different LANs. So the given address space is 172.16.0.0, which is of class B address, and we are expected to divide that into 3 subnets, and whereas in each and every subnet the requirement is given. So LAN 1 should have 50 addresses, LAN 2 should have 217 address, and LAN 3 should have 300 addresses. So what we will do is, we will first arrange it in a descending order. The largest number comes first. The largest number is 300, later it is 217, and then it is 50. So I will arrange it in this particular fashion, and then next I will have to identify how many number of bits is required to connect or to give 300 host IP addresses. So as of 300, the immediate next value what we get is 2 power 9. Exactly 300 is not possible. So we go for 2 power 9. So 2 power 9, it gives us 512. So we can create only 512 IP addresses in one block. So if that is the case, what will be the next number of bits required for the second LAN? You will have 2 power 8. So that gives you 256. And for 50, you will have 2 power 6, that is 64 IP addresses in one block. So now what is the next step? You will have to find out the first address and then the last address by keeping the host bit constant. So as you can see, the red color part represents the host part and then the black color part represents the network part. So as you can see, I am using 9 bits. When you count this, you will have 9 bits. So here this byte has 8 bits, and one more bit from here we get it as 9 bits. So this is what the starting address is, and obviously I will have the ending address. So ending address, the network part is alone converted to all ones. So in both the cases you can see that I am not altering the network part. The black color part I am keeping it constant. I am not altering the black color part. Only the red color part has to be moved from all zeros to all 1. When I do that, and then again I can convert that into dotted decimal representation, I will get 172.16.0.0 and 172.16.1.255 as the ending address. Next, /n representation is used to represent the subnet mask. How is this 23 is getting? I have 8 bits here, I have 8 bits here, and I have 7 bits here. So 16 plus 7 is 23 number of bits is being used for representing the network part. Correct. So what I am using here is the number of bits required to represent the host. So except this 9 bits used to represent the host, all other remaining bits I am using it to represent the network. That is what the principle hidden behind. And similarly for the next one, you can see that I am going to use 8 bits to represent the host, because using 8 bits in the host part will give us 256 host addresses. So I am using 8 bits over here. This is what my starting address is, and then this is what my ending address is. And even here you can very well see that the black color part is kept constant. And then you will have to write the immediate next address from here to here. So that is the relationship between how we got this address to this address. Fine. And then when you convert that into dotted decimal representation, there you can observe that the black color bits will be 24 in number. Here you will have 8, here you will have 8, and the entire byte is used for network, so you will have 8. So 3 times 8 gives us 24 bits for the network part. And then you can see the last subnetting, that is 172.16. This one you will have to write the immediate next address for this. So immediate next address, adding 1 here, all these things will become 0, and this 10 will become 11. Correct. So that is what the immediate next address for this. And once after getting the next address, you can clearly see that what will be the last address of this particular address space. And then converting that into decimal, you will get 172.16.3.0/26. So how is it 26? I'm using 8 bit. Even here I have 8, and I'm using 2 more bits from this particular part. So 3 8s are 24. So here it is again 2. So 24 plus 2 gives you 26 number of bits used for representing the network part. So that is what the number written here represents the host, and the number written here represents the network. Number of bits used to represent the network. That has to be made very clear. There should not be any confusion at this particular part. So if you keep on doing problems in this particular way, then it will be very easy for you to handle problems on the subnetting. So this is for your exercise. Here this problem will really help you to master your subnetting knowledge on this. So what you are doing here is actually we are doing supernetting. So supernetting is nothing but you will have to subnet. There are 2 stages of subnetting performed over here. The given address space is 172.16.0.0. the same class B address space is given. First of all, you are expected to divide this into 3 subnets, and then each 3 subnet will have to be further classified into 4 subnets each, right? So that is what the requirement, and the procedure remains the same. So this is what will be the answer table for the previous problem, whereas you can pause the video here and then you can go through it. So what I suggest you people is, all the viewers are expected to practice. So just don't simply take the values from this particular slide. You can work it out, and then you can cross check the answers over here. So next, there are few rules for classless interdomain routing block. So all IP addresses should be continuous, because we cannot randomly pick or we cannot randomly create the IP address block, and the size of the IP address block should be in a power of 2, which you might have known by this time. And then so you cannot ask for IP addresses which is of number 500. You can only get 512 IP addresses as a block. So that is what the size is. So taking this concepts further will have its applications on the operating systems. So I will leave it here, and then I will leave it here for your further exercises. So I'm stopping my video here. Until then, It's bye from Jai and happy learning.